Thank you very much for inviting me. I think it's a great opportunity for you guys to learn some of the most recent techniques in neuroscience for data analysis. So today I'm going to talk to you about how to analyze data in the navigation system, especially in rodents. So please interrupt me if you have questions, of course, whenever. I'm actually going to start with very simple things because I don't know what is your background, so I just wanted to make sure that we're on the same page. So I guess I'm going to reintroduce some of what Arthur introduced before. So if actually I should stay here, right? Because it's recorded, so I should speak into the mic. Yeah, okay. And I'll try not to walk too much on the stage. What? Sorry? No, it's fine. Don't worry. I'm going to put my feet here. So what the navigation system, like what are we talking about? So if you're not familiar with it, just look at this video. So I did my postdoc at NYU, meaning in Manhattan, in New York. And so when you take the subway, usually you're not alone. You have some little friends with you, very often that will visit the platform as you're waiting for your subway. But look at its behavior. It's very interesting. So it's freezing now. It's going here right next to the pillar. It waits, kind of freak out a bit, and suddenly, runs immediately to hide behind this other pillar out there, right? But what is very interesting in this video I found on YouTube, I think, is that the animal did not look around, when he was trying to find a place to hide. He just thought about the cognitive map he had from the platform. It's a very familiar environment for him, I'm sure, actually. And so he stopped there, kind of thought, he thought about it and say, oh yeah, I should go back. But he did not look back to actually think about it. Why that? Because he has a cognitive map. Right? He has a map of the environment in his head, and he can just think about it and make a decision. So this is what actually many labs in the world studies. What are the neuronal bases of such behavior and such representation? Before I move on, I just want to remind you something, which I think is very important. In rodents, like in mouse, the entire navigation system is less than 10 million neurons, right? Actually, it's perhaps more about 1 million neurons in a mouse. It can, we think, it can code for about 1,000 different maps, all right? 1,000 different environments. And overall, it consumes less than 100th of a watt, which is, to me, absolutely fascinating how, efficient the system is. Anyway, that being said, let's get a bit more into neuroscience. So perhaps many of you know already, but the navigation in the brain relies on a very wide networks of brain structures, and central to it are the hippocampus here in a rodent, and in the human brain, and the entorhinal cortex, all right? So we know from lesion studies, from many different cases, that these brain structures are essential for navigation in an environment. But it doesn't tell us exactly how this system works. So to this end, you need to go and record neurons and to analyze the firing of these neurons to understand the relationship between spike train, the spiking activity, and the behavior of the animal in its environment. And key discoveries have been made in the last 30 years. So I won't present them in chronological orders of their discovery, more in terms of, kind of complexity. So one essential signal in the navigation system is the compass, right? It's like a sailor in the open sea, or if you're in the middle of the desert, to navigate, you need a compass. And this information exists in the brain. It's amazing that it exists in the brain, and it's encoded by the so-called head direction cells. So what I show here up there, this is a tuning curve. I'll get back to it later, don't worry. Meaning the fine rate of a single neuron as a function of the direction of the head in the horizontal plane, 360 degrees, and this particular neuron fire whenever, for example, let's call it east, right? Whenever the animal faces the east direction. And another cell will fire for another direction, another cell for another direction. Altogether, as a population, they actually code for a compass. Then you have a representation of the metric, which are very certainly, we're not entirely sure about it, but encoded by the grid cells. Now what you see here is the activity of a single neuron, color-coded, meaning that when it's dark blue, this neuron is silent. When it's dark red, the neuron is active, as the animal explores a circular environment. And as you see, the firing of this neuron tessellates with triangles the environment, and they were called the grid cells, and actually it led to the Nobel Prize 3 years ago to Maybrit and Edward Mather. And the last representation, which actually was the first to be made by John O'Keefe in the 70s, are the very famous play cells. And now this is really, I would say, the end of the processing chain. It's an actual representation of the true location of the animal in its environment. Again, now the animal explores a rectangular environment in this case, and you see that this particular cell fire only when the animal is in this location. All right? So altogether, these neurons represent now a map. And these neurons are especially located in the hippocampus. So these are purely correlative studies, right? So meaning that people have put electrodes in different places and correlated the activity of these neurons with the behavior. But that already is a pretty complicated thing, and this is what we're going to talk about today, mostly. All right? So we're going to start with a very simple question. First, like, what is a tuning curve? How do we compute it? I just want to make sure. I don't want to assume that you all know how to do it. And also, how can measure the strengths, of the encoding, like how much information is conveyed by the spike train of a particular neuron regarding like a particular behavioral feature. And then we'll also look at, population activity. Now, there are many techniques that allow you to not record a single neuron, but many neurons at the same time, like play cells or head direction cells. These are two examples. And we can decode now information not from a single neuron, but from this population. So we'll talk also a bit about it. And I will very briefly, I'd like to spend more time on this, but I won't have the time. Like, what can we say about like recording these neurons during sleep? I'll just briefly talk about it, but we can talk more about it later if you want. So, again, outline of like what I'm gonna talk about like in the next 45 minutes. We're gonna start with like simply defining what's a tuning curve, how to compute it. Then like I'll spend some time about like what I think is very important to understand is information measures in neuroscience, and especially with neuronal data and what it can tell us. Then we'll spend some time to understand like how to really compute pairwise correlation, which is the first level of population neuronal population analysis. And then at the end, we'll discuss together how we can decode information from a population of neurons. All right? So let's start with the tuning curve. Very simply, most of what I'm going to present today will actually be about head direction cells, because this is a system I've been investigating myself in the last few years. And it's also make like the point very easy. It's a one-dimensional signal. But it's very easy to extrapolate anything that I'm going to say now to 2 or 3 dimensions, right? There's basically no difference. So as Arthur told earlier, just imagine that you're recording from one neuron, and this neuron spikes. It emits action potential. This is the unitary event that we detect, and we'll actually assume this is all we know about what this cell does. So we detect these times, and here you see that this neuron doesn't fire regularly. It actually fires in small bouts of spikes, and most of the time is silent. And the other information we have in this particular experiment is the head direction of the cell, right? Between minus 180 degrees and 180 degrees. So we record the animal is freely moving in his environment. We have this information. So if we want to actually look at whether the cell is modulated by the head direction, very simply what we do is that we beam all the head direction of the animal, and we count for each beam of head direction the number of spikes that were emitted by the neuron. right? That's it. You come up with something like this, for example. However, it doesn't tell you anything because this is bias. You have to correct at least for one. The first thing is the occupancy. You cannot assume that the animal has explored all the possible head directions, homogeneously. So you have to divide that, information by the occupancy, meaning the amount of time that the animal spent in each beam of head direction. You multiply it by the sampling frequency of your signal, in this case, the sampling frequency of the video, right? This is what you have. This is the information you get in time. And at the end, that results into an actual tuning curve. And in this particular case, the cell fires at 90, more than 90 hertz when the animal faces the north direction. All right? Simple, but at least I wanted to make it clear. So if you want, if you're not familiar with this kind of analysis, you can I put some very simple code to actually compute such a tuning curve, and you should actually get this figure in MATLAB if you're in this script here. Okay. If you have questions about it, I think it's better that we talk later. Later, you can come to me and we can discuss how exactly all these lines means if you need it. So this is the case for head direction cell. Of course, there are many other cells that have been described in the navigation system. As I told you, for example, place cell, the grid cell. Another one is a border cell, cells that code for a border in the environment, right? So exactly here, this is a south border cell that will fire whenever the animal explores the south border, even if you include, if you put a wall in the environment. And the reason why I'm showing you this figure, this is a typical way of representing the data when you're putting in an article. Not only you show the tuning curve, or here the place map, right, in the color-coded place map, but very, very often you also put the raw data, almost like, not entirely the raw data, but like as close as you can get, meaning in black, the position of the animal in time. This is its trajectory. And the green dots are actually the location of the animal whenever this particular cell had emitted a spike. All right? So you can you can see exactly where this place field, come from. And you see it for the grid, and you see it for the border. And it's very, I think it's essential because really you want to convince your reader that of what you're doing, and you realize also that yes, it's a very good code for the border, but also the cells was spiking. It's not like everything or all or nothing phenomenon. The cell spikes a lot also outside the border, yet in terms of fire rate at the end, clearly there's a strong correlation with the border. Another thing I wanted to tell you is that you'll see also very often that you can display occupancy. You can kind of extract with some eyebolometric, I would say, the occupancy here in the environment. Like if you look at how often the animal has visited each different location, however, it's not really quantitative. So one way that it's done sometimes, and I try to do it myself, is that actually you can use like a second dimension in your color, is that not only you color code the fire rate of a neuron, again, so gray is the trajectory, red dots are the spikes, you transform it into a rate, a color code rate map, but you can also use brightness to, for example, now code for the occupancy. Okay, so you convey even more message in a single figure, and that tells really a lot to the reader. One thing that is usually done in the field is how good is a given cell, how good is a display cell. And many criteria usually are used. For example, people set limits for to the peak firing rates. It's peak firing rate of a head direction cell. It's totally arbitrary, right? But you say, well, any cell that don't fire at least at 1 hertz somewhere in the tuning curve is not considered in my data set. In the case of the place cells, very often people say, well, I do not take into account cells that have more than 2 place fields in a given environment. Because, of course, what I showed you before, this canonical place cell, that had a beautiful tuning curve with only 1 place field is pretty rare. Most of the cells that you're going to record in the hippocampus have actually multiple place fields. And it can seem to be pretty noisy. You can also very importantly, you have to test for the stability of your representation. Meaning, for example, what we do usually is you take like the entire recording session, you cut it in 2 halves, you record, you measure, quantify the place field in the first half, and you compare it with the place field in the second half. If it's an actual place cell that does not result from, whatever bias in the data or bias in the behavior, the tuning curve should be exactly the same or very, very similar in the 2 conditions, at the beginning and the end of the recording. A last criterion that actually we're going to discuss next is information, spatial information. Say, how much information does the cell actually convey about like where the animal is in this environment? All right. So before we get more into this, I want to point out like 2 caveats, like 2 pitfalls with tuning curves, very generally speaking. It's not because you get like a great tuning curve, for example, in head direction, that the cell encodes only head direction, all right? And you have to be very careful with this. In this case, for example, the lab of the mother reported that many cells actually in the entorhinal cortex are conjunctive cells, meaning that they code for more than one, feature of navigation. In this case, they were kind of great, beautiful head direction cell. Here you see the tuning curve, the rate code. Here you actually, interestingly, they also plotted the occupancy map in a head direction on the right. But they were also spatially modulated, right? So these cells, for example, were pseudo-good grid cells at the same time. So if you had restricted your analysis on this, you would have assumed that many cells of the entorhinal cortex are just head direction cells until you actually look into the place fields, or the other way around. Okay, so it's most of the time a multivariate analysis kind of, right? So you have to be careful about it. And another issue that was raised quite recently by the lab of Fuzzy at Columbia University, very interesting paper, where he showed that actually in I would say high level, I don't want to say high level, but at least here in the prefrontal cortex of non-human primates, there were cells that will respond to sensory features in a nonlinear way, meaning they will first of all respond to more than one feature, at least 2 features, right? So it's not very clear in this example. Their people lack a very clear example, but anyway. So for example, this neuron code for 2 features that are linearly encoded by neuron 1 and 2. Okay, so this is like, let's say it's a feature, it's fine rate. So this is a very clear linear relationship. But this neuron will code non-linearly for a combination of the 2. And it's very interesting. It means that, how the way sensory features are coded or are mapped to neuronal activity is sometimes very complex and not straightforward. So the tuning curve is like one first simple approximation, I will say. All right. So as I told you now, I want to spend some time on information measure. Are there any questions about like what I just said before? No? Okay, let's move on. So information. How do we quantify the strengths of like the code, like how the quality of the code? So if you're not familiar with what is information, I'm sure like some people will disagree here, but I tried to summarize it like very as simple as I could. So first, information is, I would say, kind of a universal measure of how many different messages can be transmitted by a variable, by a sender. Information rate quantifies actually how many messages can be transmitted per unit of time. Okay, so you send a message. How many messages can you transmit? If you have now 2 agents, like a sender and a receiver, let's call them Alice and Bob, we can measure how well the 2 communicate with each other by computing the mutual information between their 2 states. So you record the states of Alice. For example, she's emitting beeps, beep, 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 beep. And you can also look at the states of Bob. He's also emitting beeps, beep, 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 beep. And you can compute the mutual information between the two and say, oh, are they communicating or not? And this is a very powerful technique, because no matter, the distribution of the data, could be beeps, it could be anything, mutual information will actually measure this communication. Actually, the maximum mutual information between two agents is called the capacity of this channel. Okay, so there's a channel between the two. Just think about the server, the YouTube server, and your screen. There is a channel, and there's mutual information between what is coming to your retina and the hard drive on the YouTube server. This is exactly, you can totally think about it this way. And as I say, so it's a very powerful universal measure that measures the statistical dependency between two variables without assuming any distribution of the samples, right? And like the exact opposite, for example, will be correlation. Correlation assumes that the variables are distributed in a Gaussian distribution. All right? So very universal. So mutual information. So if we get a bit more in the math, if you don't have any background in math, don't freak out. Just read with the roads. So this is one way to actually it's not one way, it's the only way to describe what is information. So if you really wonder what does it mean, I don't want to spend too much time on it, but basically is what is expected. So P is like the probability of the state of a variable X, a capital X, okay? The log of P measure basically the number of states in which this variable can be, and that entire thing basically measure what is expectancy that the variable X will be in some states, right? So what is basic, in other words, is like what is the maximum amount of information I can extract from reading the code of variable X. But this is only for one variable. If you then compute, if you then actually look into mutual information, you need two variables. And the mutual information, one way to understand it is that if I listen to Y, the Y variable, I can compute the amount of information that is, I can extract from Y, and I subtract from it the amount of information in Y that I can predict from what I know about X. Okay? And that gives you exactly how much is communicated from X to Y. Okay? So this is it here. And you can write it in this complicated way in terms of probabilities. But if you're curious, if you don't know anything about it, if you're curious, just Google it. You have 1,000 websites that will tell you exactly how to interpret this equation here. But one way to interpret it, this thing is that if you know everything about Y, just by knowing X, right? X equal Y, that's an example. Then this information here is equal to 0. There's no more information you can get from Y if you know everything about X, and then the mutual information is just equal to the information you get from Y. However, if X and Y are statistically independent, totally independent, it's exact opposite now. Everything you know from X won't tell you anything about Y, meaning that this value now is equal to the information contained in Y. And the mutual information is equal to 0. All right? So, seems complicated, but let's take a very simple example. Let's take a place cell. Now you know what is a place cell. That will fire constantly in 1/2 of the environment. So this is an environment. The animal, runs there. And let's assume first that the animal visits he spends as much time in the left as in the right half of the environment. And that when the animal is in this part, the cell will fire at a constant rate that I call R. R can be anything, above 0. Okay? Just constant spike rate. I can compute easily what is the probability that the cell is active, that the probability that the animal is on the right side is equal to 1/2. Probability that the animal is on the left side, this is a probability that the cell is silent, is also 1/2. right? The sum of the two probabilities equal to 1, sure. And then the information, very simply, if you remember what I told you before, that the sum of these two possible states, right? And if you do the math, is equal to log 2, which is by definition 1 bit. So in case you have a place cell that tell you if you're like with very high reliability that you're in 1/2 of the environment, it will give you 1 bit of information. That's it. All right? So can anyone tell me how much information I will get from a cell that will fire in 1/4 of the environment? Just imagine now that the cell fire only in this upper top corner here. How much information will I get? 2 bits. Yes. Why? Because now I don't have 2 states, but 4 states. And in 4 states, only 1 will actually lead to the firing of the cell. So now it won't be log of 2, right? It will be log of 4. And well, then I'll get 2 bits of information. And so on and so on. Because, sorry, actually, so I skipped a bit of details here, right? But information in bits, that's on the basis of 2. So basic, it's always binary, 0 or 1. So if I have only 2 possible states, this is 1 bit. If I have 4 possible states, it's 2 bits. All right? So a message that conveys 1 bit of information is a code that reliably informs you about 1 in 2 states. Whenever the cell fires 1 spike, it transmits with absolute certainty the location of the animal. All right, in this case. Whenever you hear 1 bip on the loudspeaker, the cell has fired, you know that the animal is on the right side. However, the neurons fire at the rate R, meaning that the neuron transmits R bit per second of information, of spatial information, but only 1 bit per spike. You see the difference? 1 bit per spike in this case, but because the cell fired R hertz in this environment, it transmits R bit of information per second. But in reality, of course, a neuron first does not, have only 2 states of firing rate. It's graded, it's distributed, and the animal does not occupy the space homogeneously. So then you can also do the math, and this Bill Skaggs did it the first in 1993, and basically it's like when you know a bit about like the math behind mutual information, it's very straightforward. Basically, it came up like with a description of mutual information between the spikes that you detect and the spatial location of the animal. And this is a direct application of the formula, the mathematical formula I showed you before. And in this case, this is so the probability of spiking knowing the position times the probability of being at somewhere, and the log of the ratio between these 2 values and the probability of spiking. But if you assume that the neuron is a Poisson process, all right, it's a very good assumption for many neurons. And in this case, you can assume that the probability that the cell spike knowing its location is just equal to the firing rate of this neuron times the time bin that you have chosen. You have to choose a time bin, like you observe the state during a certain time, delta t. And this will be directly related to the probability of emitting a spike. This is a definition of a Poisson process. The probability that, the prior probability that actually the cell spikes overall is just the average firing rate of the neuron times the same interval. And here, this is just the occupancy map. What is the probability that the animal is in one location in the environment, all right? So you can rewrite it. It's just that the information, the spatial information transmitted by one cell, whatever cell actually in the brain, is the sum for all location of the firing rate of this cell at location X, and the log of this ratio, meaning the firing rate in this location divided by the average firing rate, and all multiplied by the occupancy map, all right? And then that gives you an information rate, meaning in bit per second, okay? Because you basically, you get rid of the delta t term in this equation compared to the previous one. And if you divide this information now, again, by the average firing rate, that will give you the information per spike, Remember, that cell that fired only in the right half emitted 1 bit per spike, but was emitting R bit per second. All right. So again, if you run this code here, you'll see it's basically everything I just said is only 4 lines in MATLAB. That's pretty simple when you know the math behind. It's just a direct application of this. Again, we can talk about it, but as you will see, like the probability of occupancy is pretty straightforward. There's just a very little trick of linear algebra here to express like a sum over all the different positions just as a dot product, because MATLAB is really good at linear algebra. So whenever you can write something in terms of dot product of vectors instead of sum, and that will be much faster. So you don't need to go through a loop. And at the end, you just divide by the average filing rate of R here, and that will give you the information. All right? So if you run it, sorry. I think I talk about it later. Oh, yeah, I talk about it later. But for a head direction cell, I guess the one I give you in the data, you will typically get like 1 bit of head direction per spike. Okay, so this is like a very normal value to get very. I'd say this is what you get in average, 1 bit per spike, meaning that of course the tuning curve is not 1/2 of the 360 degrees, but because the spike train is also noisy, even if you have like a tuning curve that is pretty narrow, like let's say 60, 80 degrees, right? Because of the noise and because of the width of this tuning curve, in average that will give you 1 bit of information, meaning it's the equivalent of a cell that will fire very reliably, absolutely reliably, in 1/2 of the 360 degrees. If you follow me on this, okay? So it's a very interesting measure to compare the code of the neurons that you record in different areas in the brain. For example, in that paper 14 years ago, you say that they compared the distribution of information, spatial information in bit per spike in different structure in the brain. They make the point like they wanted to actually show that there were places in the navigation system that are very devoted to representing the location of the animal, so while some other actually were not, even if they were really close by. And they compared this distribution. So you see here in CA1, so this is the hippocampus, place cells. Okay, below you see actually the occupancy, so the path of the animal, the spikes, and you see that the information is very, very high. I mean, it goes to 1, even more than 2 bit per spike. And then you have the MEC, medial entorhinal cortex, where we can detect grid cells. It's a bit less, all right, but still pretty high. However, right next to it, in the lateral entorhinal cortex, is really low. And that was a demonstration that actually in this pathway, these are 2 parallel pathways, the LEC does not convey any information about space. Okay, so that was a very, I think, a very clear way of demonstrating this feature of the navigation system by this lab. All right. One thing I wanted to point out, which is kind of related to what I told you about the tuning curves, is that you always have also to be careful in terms of how you interpret the amount of data you get. Because if you understood what I just showed you, is that there is a very strong relationship between the tuning curve and the information rate. Information is directly actually read out from the place map. So this is something that we studied like recently. And we showed like this particular feature is that if you look at this head direction cell, and we were pretty sure it was only a head direction cell, and now but we looked at where it spiked in the environment, okay, and clearly it was not uniform. When we computed the amount of spatial information that this cell transmitted, it was pretty high. I mean, it was above 0.5 bit per spike, which we consider as pretty high information rate. Okay, so I was kind of puzzled by it. I was like, well, how is it possible? But other people had the same observation before. But then if you generate an artificial spike train, which is based on what? Which is based only on the tuning curve and on the observed head direction of the animal. Okay? So you can generate like a spike, like a firing rate. You read out at each time, you read out the head direction, and then you read out the firing rate that you expect from this cell. So you generate a predicted rate from which you can actually draw a Poisson process, and you can build an artificial spike train. So in red, this is the one we observe, and in black, this is the one we generate here. You can generate another place field here, and you see that it's exactly the same. It's exactly the same. So again, this cell, by construction, is a pure head direction cell because the spike train was generated only from the tuning curve, okay? But what we observed is that now the spatial information contained in it was also very high, even if it was a pure head direction cell. And the difference between the two was very low. And I don't want to get too much into the details here, but the conclusion was that the problem here is that the behavior is not homogeneous. Is that in this particular, in this square environment, the animal tends to run a lot along the walls. So along the walls, the distribution of head direction is not homogeneous, and meaning in the case of a cell that fires for like the north direction, it will fire a lot along the walls. And that fact only actually generates spatial information. Again, I don't want to get into the details here, but what we conclude, though, is that what seemed to be like a bug in the analysis turned out to be a very interesting way to generate spatial information that is actually used by the brain. So because of this bias, the brain actually uses it to extract spatial information and build a spatial code directly out of it. Anyway, long story short, we can talk more about it later if you want. Let's move on. It's already 20 minutes left. So caveats about it is that the information, the way it was computed, it depends on the bean size. It depends on the size of the beans you choose. So, and it's very sensitive to it. And as I just told you, it's it's sensitive to an homogeneous sampling of the data. So one way to actually get around it is to use cross-validation. So what do I mean by that is the following. Just imagine you take some of your data, actual data, we will call it training set, and we observe the head direction, we observe the spike train. So from this training set, we build a model. In this case, the model, so sorry, there's a bug here. In this case, the model is a tuning curve, all right? So this is your model, like this is the way you model the spike train of this cell. And then you're gonna test this model against the data you record in a test set. So a test set is some other part of your recording. You also have the head direction. You also have the spike train you observe. And you test how well this model actually fits with your spike train, like the observation of the spike train. So in this case, you see that for this direction that I actually drew in PowerPoint, it's not actual data, you see that the rate increases at different points, and that actually matches the times where we see increased number of spikes, okay? So how do we actually test it and measure it? And how do we measure the quality of the fit? Well, again, it's like a lot of math. Don't necessarily want to go through it, but basically you can compute a so-called likelihood function for a Poisson process that has this form here. You can take it for granted if you're not interested in where it comes from. And interestingly, so that will also, it's also an information measure. So it will tell you, well, this is how good my model is. But you need always to compare a model with a null hypothesis. And in this case, the null hypothesis is that the rate is flat. It does not depend on your behavioral feature. It does not depend here on the head direction. So it's the average firing rate. The cell will fire the same rate for all possible head direction. So we called it here, this is the likelihood function for my tuning curve f, and I compare it to my tuning curve 0, meaning flat. And the difference between the two is actually the amount of information I get by actually assuming that the cell is modulated by my behavioral features. Okay, so this is a difference between this and now a fine tuning curve that is flat and that we call F0, so it takes this form. Okay? And this is actually has a dimension also of an information, like you can express this in bits. So, so I told you about this training set and the test sets. How do you do it? Well, let's imagine this is the entire data set, and usually you do it like 10-5 or 10-fold cross-validated procedure, meaning that you take the first 10% you take the 90% of your data, you build a model, you build a tuning curve, and you test it on 10% of the remainder data, the test set. And you do it for the first 10%, for like, the other 10%, so on, so on, so on. You do it 10 times. You average your values, meaning like how well your model is, and that will give you actually a good idea whether this cell is actually a head direction cell in this particular case or not. So if you run this MATLAB code, this is exactly what is it will be done in the case, again, of a head direction cell. And you'll see that it will give you the same amount of information that was previously given by the mutual information measure, like about 1 bit per spike. So why it gives us the same thing? Well, we know these cells really code for head direction, almost only for head direction. The sampling of head direction is pretty good, so there's no bias in this regard. And the parameter that we chose, meaning beams of 6 degrees, is good enough to actually capture the entire variance of the data. But one interesting thing with cross-validation is that you can now vary one parameter and test different parameters and see, look for the one that actually best explain your data to optimize, for example, the resolution of the tuning curve. So, for example, you can run cross-validation for different size of the beams, of the head direction beam, and you will see it's not very clear here because, again, head direction cells are so clear, but in this case, you will see that the best cross-validation is for beams of about 6 degrees, right? So this is amount of information for different beams, and you have a maximum around here, okay? And then, of course, if you use very large beam, you're going to lose actually information. So that, again, will tell you how you can look at your data. You can do it with splice cells that was done by Ken Harris in his 2003 paper. So, for example, you observe a place field, and the question was how much should I smooth it to actually extract, useful data? And here it's not smooth enough. Here is actually the smoothing is too large, and by using cross-validation procedure, you can actually find the most optimal kernel, 2D Gaussian kernel, to smooth your place field, in this case, which was 5.5 centimeter. All right? So a very powerful method. So summary here is information, powerful measure to study the mapping between spike trains and internal or external states, very generally speaking. And you have to still use it to be careful. Information depends, on the choice of binning. However, you can use cross-validating measures to get better estimates. All right. Any question about it? I know I spent a lot of time, but I think it was important. No? Okay. So let's move on. In the last 10 minutes, let's talk a bit about the pairwise correlation, but Arthur talked quite a lot about it already. So again, this is I would say the first level of population neuronal population analysis. Just look at neurons, 2 by 2. So again, very simply, just to make sure we speak the same language here, just imagine now you don't record one cell but 2. They emit spikes in time. So what you can do, you can bin the data in time, all right, in small windows. You can compute the number of spikes in each window, and then you report these numbers in a 2D graph, for example, here, and you see that in this particular example, these two cells are correlated, meaning that when one cell fires, the other one fires. When one cell is silent, the other one is also silent, okay? So here, the linear correlation is almost 1. Okay, we don't know why they are correlated. We just observe it. So this is for zero-like correlation. So you look at the correlation, beam per beam. Another way also you can do it now that gives you even more information, you look at the correlation not only at time 0 here, but as a function of time lag between the two spike trains. So this is a cross-correlation function, meaning that it's a correlation. So what is the amount of correlation between the two spike train when you jitter one spike train with the other by a certain amount of time? And interestingly, first is that at infinite time, you know that this correlation is just chance, okay? So if you wait like 2 hours, there's no reason why when you jitter a spike train by 2 hours, there's still a correlation in it, right? And here, this is like the correlation I just explained, time 0. But interestingly, you can actually say a lot about like the width of this cross correlation. That will tell you actually how much time cells usually are activated together, right? So it's not it's not only how much they are correlated, it's also how long they are correlated. Okay, I'll show you more examples after. Here's another example. This is exactly opposite. So when one cell is active, the other one is silent, and vice versa. So this is a negative correlation, okay? And now, if you look at the cross-correlation, it's not a peaky cross-correlogram. Now there's a deep. So again, this is like a chance value here, you know, at infinite time lags. But around 0, the correlation drops. And again, the width of it tells you how long usually this negative correlation lasts. And third, of course, you have the uncorrelated case where basically the spikes seems to be totally independent from each other, and so there's 0 correlation and the cross-correlogram is flat. So in case of head erection cell, which again is a really nice way to look into it, for example, for these two cells, if you run this code, you will see the two tuning curve, and you can compute the cross-correlation, not only as the animal is awake, but also during sleep, okay? So as you expect, first, these two cells fire for like, you know, for the same direction. So when the animal runs, so the animal is awake, is exploring, if you look at the blue curve, you know, you see that these cells are correlated with each other. Of course, they fire together. They fire whenever the animal faces this direction. And you see here the width, which is about 2 seconds, let's say, all right? Well, this is just behavior. Right? This is the amount of time, in average, the animal spends in 60 degrees of the head, right? So he looks here, he moves a bit, then he looks over there, and moves for 2 seconds, all right? So this is what you can extract just from the cross-correlation between these two neurons. Interestingly now, if you look at the cross-correlation between these two neurons during sleep, it shows you exactly the same thing. If you look first during REM sleep, rapid eye movement sleep, which is an activated state of the brain, which is virtually indistinguishable from wakefulness, the two cells are activated exactly the same way. They are still coordinated, meaning that this coordination somehow is hardwired in the circuit. And on top of that, they also spend the same amount of time spiking together. In other words, like REM sleep, like when these mice were kind of dreaming, they were dreaming at actual speed. Like, you know, during the spontaneous activity, they will spend the same amount of time virtually in each of these directions. During non-REM sleep, or slow wave sleep, which is the other half of sleep, this coordination is also preserved, but is compressed in time. Now everything goes, you know, much faster. I will show you some more examples. It's another example here. If you uncomment like one line, which is called cell IX in the MATLAB code, that will generate this second example. These two cells now fire for opposite direction of the head. As you expect in blue, during wakefulness, these two cells are, in blue, are anti-correlated. They never fire together. Okay, so there's a dip in the cross-correlogram. And you saw also a dip in the cross-correlogram during REM sleep, during non-REM sleep, but again, the width is different because the underlying dynamics is different. All right? So it's best explained, so best actually seen from a video. So what you see here, the animal explored like, you know, some open space, like open air, arena. So, but you're only going to see actually its head direction. Okay? Here what you see are like about 20 head direction cells recorded simultaneously. We don't show spikes, we just show like smooth spike train activity. And the cells are sorted by preferred direction, meaning that two cells, like two lines, represent neurons, are two neurons that have mostly overlapping tuning curves. And this is local field potentials in the hippocampus, which is a good, like, you know, indication of the brain state. So the animal is awake, so it's not very surprising now that you see there's a packet of neurons, a group of neurons that is your needle that codes for the direction of the head, right? So you can reconstruct that probabilistic, you know, head direction just from the neuronal activity at any time. So this is what is shown here. So basically you can reconstruct this needle. Okay, so you record these neurons. There's only one group of neurons firing at any time, representing like the current direction, and you can reconstruct it very reliably. Now, of course, the question is like, what happens during sleep? As I showed you before, it seems that this code, let's call it this way, is preserved. So this is the same neurons, same animal, now recording during sleep after the task. And the first half of the video, the animal is in non-REM sleep. And so, don't want, like, long story short, like sleep always starts with non-REM and then REM. And you'll see that halfway through the video, I will show you when the brain will actually shift into REM sleep. So, and this is like, so non-REM in the hippocampus, you have like very large wave and fast oscillation. And then during non-REM REM sleep, you will see, you'll have these very rhythmic so-called theta waves. So you see this is non-REM, so you still have at any time one packet, but it kind of jumps from one position to the other or sweeps very quickly between different directions, right? So everything seems to be much faster, a bit noisier as well, but it's always preserved. At any time, we always have one packet. And suddenly you're going to start seeing like these first theta waves in the hippocampus. So this is the beginning of REM sleep. This is a transition. And you see that the needle kind of stabilizes. All right, so this is the beginning. And now you have big theta waves in the hippocampus. You have, like, the head direction is stabilized and start drifting. But now it starts drifting much more slowly, right? And actually, if you compute the average speed at which the needle moves during REM sleep, it's exactly the same as during wakefulness, meaning that the system knows, basically, the statistics of natural movement, okay? Okay, again, we can discuss it more if you want later. I'm not going to talk about it. Arthur already made the point. Looking at correlation is also a very good way to compute and quantify how coordination that appear during wakefulness, especially in the hippocampus, are replayed during subsequent sleep, and we think that it's a sign that information is replayed in the brain, and very likely this is important to consolidate our memories. Okay, but that's not the point today. So, again, summary. So pairwise correlation is a simple, straightforward measure of how two neurons are coordinated. It informs on the tendency of two neurons to fire together, that's positive correlation, or to be mutually exclusive, to fire in a mutually exclusive manner, negative correlation. The cross-correlation, meaning correlation in time, is a very simple indication of how of the typical duration of this coordination and how long two neurons fire together. However, I haven't had the time to discuss it, but this correlation, you have to be very careful because they depend on the firing rates. And they also result on not only the signal, they result actually on both the signal, meaning the tuning curve, like what this neuron code for, but also the so-called noise correlation, meaning like non-specific noise, you know, for example, the slow activation during sleep that will make up the correlation. So again, being careful of how to study it. So as I expected, I won't have the time to talk about the last point, which is fine. Very quickly, I wanted to talk about Bayesian decoding. So Bayesian decoding is, as I showed you in the video, one way to decode from population activity the information that is encoded. In this case, for example, you can decode the head direction from the head direction cells. All right, and you can do it, of course, as the animal is awake, but also as the animal is asleep. And I actually also realized this morning that I forgot to put this MATLAB code online, so I will do it this afternoon so that you can have it. That being said, all the data of the head direction cells, so you have like few cells on the data, but everything is available online, and all the code is also available online if you want to dig into it and play it with it yourself. Okay, so thank you, and if you have any question, I'll take it. What would I do that? Like what?
I guess seeing your talk, I noticed that there's lots of this conjunction cells
Yes.
are coded for head.
Yes. Yes.
So maybe a way to tease apart the.
Yes. Well, this is exactly what we're trying to do now. But like, again, you have to keep in mind that there are many ways to test it, right? In the lab, you can try to head fix the animal. You can try to actually move the visual cues and see how it affects, the coding, for example. But any test, any manipulation you do, then is actually very non-natural for the animal. And for example, when you test like in a head fix navigation, you can do it in virtual navigation. Many people do it, and it's a very powerful method. But you lack like very important signals in terms of vestibular vestibular inputs are not all gone, and we know that actually the system does not really is not really activating in the same way as it is naturally. So it's a very complicated issue. But yes, we can try to tease it apart, and this is what we're doing as in science. Yeah.
So I would request the student and the attendees not too shy. So please ask questions even if you don't think it's very sophisticated.
Oh yeah.
So please, any question? If not, yes, you know.
Just wondering, in practice, when do you run into big differences between using the
That's actually a very good question. So it really depends. So like for example, like let me put it this way. So like computing a correlation between, for example, like the spike train of a cell and its spatial location is not straightforward, right? So it's hard to actually come up with a measure of direct correlation between the two things. So mutual information in this case seems more natural. Correlation, when you have like one observation and a second observation, it's easy to compute the correlation, right? In the general case, it's always better to use mutual information because it does not depend actually on the structure of the data itself. So it's straightforward. You can always express like any kind of data in terms of probabilities, and so this is why. And you could try, but then it will be so biased by different things that you'd better not. Again, in the case of the head direction, though, it's so simple and it's so straightforward that it will work the same. All right. So it's better. Many people actually don't do it, but it's better. And especially, well, at least you have to come up with some, statistical test of like how significant is your measure, right? It's not because you observe like 1 bit per spike that actually it means anything. So you have to either use cross-validation, or you can actually use shuffled data in kind of the same spirit as Arthur showed before, but you have to come up with a test. So, but I'm saying it, though, like all in the field, many people will just report, as I showed you the distributions, like, oh, this is spatial information. As good as it can get, right? But yeah.
similar question about separating the head versus
Yeah.
variance in the signal. Have we tried that statistically to show over
Yeah.
and above the variance accounts for the grid cells specifically?
Yeah. So there is a very straight. So I didn't say anything about it, but there's a very straightforward. I would say the most rigorous way to test it is to actually, for example, compute like a 3D tuning curve in this case, right? And you can really actually tease apart, the contribution of space and head direction. So imagine that now you compute like a 3D matrix kind of place for each head direction. You can compute like a place field for each beams of head direction. All right? And then basically you can study it and say how much actually is explained by space or by head direction. However, the problem is that you'll always run into the problem of sampling. Because to actually have a good estimate of this 3D tuning curve requires the animal to run like crazy for like 45 minutes, even in the 70 centimeter environment. So it's never the case. It's never the case, and this is one of the biggest problems. So then there's a lot of papers that actually came up with, with methods to measure information with low sample data. So there are many methods, but it's very sophisticated. And then the problem is that you run another problem is that people start not trusting your analysis, say, well, you're using these very sophisticated tools. I don't understand it. I don't trust it. So this is why sometimes you have to find kind of shortcuts, I would say, that are not necessarily the most rigorous, but at least it's easy to explain and it gives qualitatively the same result.